Okay, so we're now going to think about Boyle's law, but in general terms, there are 4 variables that are needed to define the physical state of a gas. We need to know the temperature, pressure, volume, and the moles of gas present. Our first law is the pressure-volume relationship for gases. And the British chemist Robert Boyle, who lived a very long time ago now, 1627 to 1691, first investigated this relationship between the pressure of a gas and its volume. And it was really a renaissance period for science, because we'd got rid of this ancient Greek idea that science was not, or our understanding of science was not advanced by theory, but by practical experimentation. And so there was this real flourishing of experimentation. And chemists at this time would make their own equipment. So if you needed glass chambers to hold gases, then they would be handmade, or blown by the chemist or by their assistants. So I think it was a really exciting time as far as our development of understanding of science is concerned. So Boyle's law states that the volume of a fixed quantity of gas. Now, how would we normally express that? What does that mean? In terms of chemistry, we've got a fixed quantity of gas. So this is one of those times, Brio, where you would fast forward through the awkward silence. Does that seem reasonable? We're keeping the number of moles constant, because remember, these are our 4 variables, and we're looking at volume and pressure, and so now we've said that the moles have to be kept constant, and we've also said I think I might have written down the wrong volume, maintain a constant temperature. Sorry. Yeah. These two have to be kept constant if we're looking at the relationship between those two. Does that seem reasonable? If these are our 4 variables, it's going to keep 2 the same, and we're only going to look at the relationship between the remaining 2. That does help if I write the correct word up here. Okay, so what this means is that if I multiply the pressure in the volume, I will get a constant value, no matter if it's, as long as the temperature is the same and the number of moles is the same. If I increase the pressure, then I have to decrease the volume to keep the, because of this. Okay, so if this one goes up, this one has to go down. And if this one goes up, this one has to go down. Does that make sense? Because we're saying that when we multiply them together, we have a constant value. So we can rearrange that and say that V is equal to a constant multiplied by the inverse of pressure, and we could also say that the pressure is equal to a constant multiplied by the inverse of volume. Works both ways. But where we normally see it in our calculations would be in this form here. P1 V1 equals P2 V2. Okay, so as I said before, with these qualifying statements that the moles and the temperature have to be constant, we can then just look at the relationship between pressure and volume. So this relates then to one gas, 2 conditions. That's what this means here, that I've got my sample of gas and I'm putting it under 2 different conditions. And I'm looking at the relationship between those pressures and volumes for that one gas. Now there is an example calculation on page 12 where it says a gas occupies a volume of 2.12 litres. So we've got our gas, and I'm going to call that V1, 2.12 litres. And the pressure, P1, is equal to 101.3 kilopascals. What will the new volume be? So I know I'm finding V2 when the pressure of the gas is increased to 202.6 kilopascals. Well, we've increased the pressure, haven't we? So we can tell that we're going to have to decrease the volume. And because we've doubled the pressure, we're going to have to halve the volume. I can do that in my head. But let's go through and put these in. Using P1 V1 equals P2 V2. We're going to want to find V2. So I can just rearrange quickly and say that V2 is equal to P1 V1 divided by P2. And then I can substitute in V2 is equal to 101.3 times 2.12 divided by 202.6, and that will give me a V2 of 1. Oh, gee whiz, I'm out of practice of writing on the board, aren't I? 1.06 litres. So we doubled the pressure, we halved the volume. Can use this only here, only when we're not fiddling around, like we have the one gas. N must be constant. We can't use it either if T varies, if the temperature varies, because that's going to change the kinetic energy of the gas molecules.